Welcome back to Cody's Lab. So if you've been watching my channel for a while, you might have seen me distill alkali metals a few times, notably in my 1 million subscriber special. Now, in the past I've used very crude setups using plumbing parts, as were very inefficient. I would lose a lot of metal in vapors as it escaped out the threads. It still worked, but I'd like to try making something a little bit better. So I thought today in this video I would try to invent something that is better. No guarantees that it will be, but at least we'll get to see the process, do a little bit of science along the way, and see some reactive metals. So real quick, I need to explain a little bit of chemistry. So if we have some potassium metal plus some sodium chloride, so that's normal salt, potassium is a more reactive metal than the sodium is, so it's going to steal away the chlorine to form potassium chloride and sodium metal. Let's say I have sodium and potassium chloride, but I want the potassium metal and sodium chloride. Well, fortunately, this reaction, like all reactions, is reversible. It goes both ways. It's going to end up in this direction more often than it is over here, but both directions will occur. So if we can remove the potassium from the equation as it forms, we can drive the reaction this way more than this way, forming the sodium chloride and potassium metal, even though this direction is more favored. Now how can we do that? Well, one way is the fact that potassium has a lower boiling point than sodium. So it'll boil away before the sodium will, so we can remove it from the system. In that way we can convert sodium metal into potassium metal. And what we are doing today is building an apparatus to do just that. And of course, you can replace these metals with other metals and it still works. So, what am I thinking for the apparatus? Well, in the past, I've just had basically a tort. It looks like this, has a spout coming off the top where I can collect the metal in a container. And I have some sodium mixed with some potassium chloride. Heat this up, those will react, the potassium will boil away and come out and collect. First of all, I mentioned earlier I was using pipe fittings which have threads, and it's not like Teflon tape can handle the kinds of temperatures we're working with, so some of the gas will escape and also oxygen can get in. Further, it's quite dangerous. If this gets plugged up, then there's nowhere for the pressure to go except for to explode the vessel.
There, and it just blew something up. Shoot.
So, new design time. Let's say I had basically the same thing as before, but this time have the pipe come in from the bottom of the vessel so that when your reactants react and form the metallic vapor, it goes up and then down like this. So now it's hot for this entire section. There's no bends or anything where something can get trapped and the metal falls straight out. It's unlikely to get plugged. Still possible to get plugged, but less likely. Now, because it's still possible to get plugged, let's say we just have a lid that fits on like this down in a bath of a liquid. So now this can easily move in and out. If pressure builds up, it'll just lift it off the top. It's not going to explode the metal, or it'll just push the gas out through the liquid. So this design is much safer, and also the liquid's going to make a perfect seal, keeping all the oxygen from entering and all the vapor from escaping. So something like this is what I'm going to try to build today. So first of all, I need to remove the zinc coating from any metal parts that I'm using. Zinc will become a contamination, and also the vapors could be a problem while I'm welding. Then it's just a matter of cutting everything to fit and welding it together. And here is the final product. Let's zoom in a little bit. You might be able to tell that I welded the top here before I welded the bottom, because the weld on the bottom is much nicer. I was much more in practice at that point. Let's open it up. We'll see inside. Yeah, it's a little off center, but it still works. See, I got a little mark here and a mark there, so I can line it up so it fits the best. Also, I've added some tacks just so it doesn't go all the way down, because once it goes all the way down it tends to stick and it's hard to get back apart. So now it won't go all the way in. This makes it much easier to get back apart. Yeah, pipe's welded in there. Everything's watertight at least. Should be good to use. It is mild steel. I would prefer it to be made out of stainless steel, because the mild steel is going to flake away after a few uses. But this ought to be a good prototype to see if this design works. If it does, maybe I'll have somebody make one out of stainless for me. I don't actually have the equipment to weld stainless at the moment. I need some cesium for an upcoming project, so let's put this to use and make some. So first of all, I've got some cesium chloride in there and some lithium metal. So I've just weighed out the ingredients. I have 3.5 grams of lithium metal, which weighs hardly anything, and 84 grams of cesium chloride. So now all I need is the liquid to fill up this groove and seal the chamber, so that when I put this on, it's airtight. I have some tin here which I will melt and pour in, but there's one problem which I have identified. In my testing I have found that tin, and every other metal I've tried, absorbs the alkali metal vapors, forming this material right here. This is tin and potassium. Heating the tin to the boiling point of my alkali metal won't necessarily drive it off. It'll actually stay collected in there. In much the same way that water from the air will absorb into a bucket of potassium hydroxide that you left the lid loose on. It's very hard and brittle. Also, it tarnishes easily and releases hydrogen on contact with water, as you'd expect. This is kind of an interesting material. It's not a huge problem, but this does mean that I'm losing some of the metal. Fortunately, I've thought of a fairly simple solution, and that is just to add a little bit extra cesium chloride on top of the tin. Cesium chloride will melt and presumably form a barrier which will keep the metals apart. Well, without further ado, let's melt the tin. See, that's why I'm using tin. It's very easy to melt even with a blowtorch. Also, it's non-toxic and has a low vapor pressure. Probably a good idea to warm up the chamber a little bit so the tin will flow in better. Don't want to get too hot and accidentally ignite the lithium though. Okay, in goes the tin. Just like so. A little bit of the cesium chloride. Piece of paper to burn up the oxygen. There we go. And seal. Nice. I think that worked. I'll let it cool off. Make sure the... Actually, I can just look with my light. Okay, yeah, it's definitely sitting in the liquid tin. So this should be ready. I've drilled a hole in this insulated brick here so that the tube can fit down through, just like that. Got another bit of insulation right there, which helps lift it up into the furnace, which I have right here. I've removed the lid, so I can just take it, turn it around. I should be able to slide it right over top of my little apparatus. There we go. What's wrong with that? Nobody ever said that the furnace has to be upright. Plug that in. So the idea is that the cesium vapor will come up and then down this tube, and then because the ambient temperature is much lower than the boiling point of the cesium will condense and then drip down into this little bottle I have with some mineral oil. We remove this plug. This tube here I've got connected up to a bottle of argon. So we just stick this down in there. You can see I got a very small amount of argon bubbling out. That'll help displace the oxygen and keep the cesium from igniting. I can take this lab jack, raise it up so that there's no distance between the bottle and the tube. I'll also add a little bit of fiberglass just to slow down the diffusion of air. Okay, that should do it. Let's turn on the furnace. There we go. What temperature do I have that set at? 1600? Yeah, we don't need that hot. Let's bring that down to about 1400 F. That should do it. Okay, so I'll just stand by, keep an eye on things, have my fire extinguisher ready, and hopefully I won't need it. So that's the boiling point of cesium. There's nothing coming through yet though, because, well, the thermal probe is on the outside of the chamber, and it's of course going to take some time for that heat to get in. The cesium chloride on top of the tin is probably melted though, so that's good. Yep, still got the argon going in, all the oxygen should be displaced by now. That's kind of cool. I have cesium. Nice. Well, seems to be done. Cesium hasn't dripped out in a while. You can see the stalagmite that was forming tipped over. Let's cork the bottle, shut this down. Okay. By cork, I of course mean a ground glass stopper. There it is. Such a pretty metal, isn't it? Approximately 23.6 grams of cesium. So that's a yield of about 35%. That doesn't sound like much, but when you compare it to the 25% yield I was getting before, this apparatus has done better. So now I suspect there's a problem. If it was just the tin, I'd just let this cool off and then I'd be able to open the chamber without any trouble. But since I added the cesium to the tin and the tolerance is so tight, if I let the salt solidify, I might not be able to get it back apart. So I'm going to have to open it while it's still hot. If there's any lithium left, it will ignite. And lithium burns quite hot. So hopefully that doesn't happen. It's nothing I can't deal with. So let's just pull the furnace off and open the chamber. If I make another one of these, I'll increase the tolerance so I don't have to do this. Okay. Let's see if we can open it now. Ha! It opened. Easy peasy. Nice. I'm going to pour the salt out into my little mold here. And a little bit of lithium left over by the looks of it. Something. Yeah. There's my lithium chloride, probably a little bit of cesium chloride left. After dissolving away the salt with a bit of water, I'm left with the tin. And it looks like it's pure tin too. There's no alkali metals dissolved in there. So the cesium chloride treatment seems to have worked. Nice. And of course, I can reuse this. And speaking of reuse, I can, of course, just take a wire wheel or something to this, clean it up, and reuse it. In fact, what you saw was the third time that I've reused this thing. There are a few things I would like to improve, though, and that is, first of all, this gap here needs to be larger so that the pieces are easier to remove from each other, especially when I'm using salt. And mild steel oxidizes and flakes away, so eventually this is going to get very thin. Stainless steel wouldn't do that. So yeah, that's pretty much all I got for now. Hope you enjoyed. I'll see you next time.